and how they connect to rock deformations. That's where we're headed. And one of the ways we get to that is a graphic representation of this on something called Morse circle. So that's kind of where we're headed in this particular discussion. Now, just to review a little bit about the deformation experiments, it's important to why they're set up the way they are. They're set up with a geometry such that the stresses in the system can be considered two-dimensional, or what's called plane stress. Note, it's very important to understand that plane stress is not the same as plane strain. Plane stress is axially symmetric strain, or stress. See, I said it wrong. Axially symmetric stress, where in the cylinder, on the axis of the cylinder, the stresses are all the same, or the loads are all the same around the sides of the cylinder. And the only difference is the end of the test specimen. So if you look down on the axis of the cylinder, any planes that are parallel to the axis of the cylinder have exactly the same load across them. That makes the stress a two-dimensional state of stress. And that matrix, for example, that we were talking about is a 2x2 matrix instead of a 3x3 matrix, because the others are just redundant. In this experiment, you can modify the pressures, so you're changing that condition, but they're also set up so you can modify other experimental conditions, like the temperatures can be modified, the fluid pressures, which we'll talk about later, can be modified, which have a big influence on the deformation, and you can control the rate of deformation. This doesn't necessarily matter much when you're breaking rocks, but it does when you're making rocks flow, and we'll get to that as we go along. We already said that about the different conditions of this problem. So what are the properties of this load? So this is a good way to think about how stress systems work. If you just make a cross-section of that test specimen in this experimental apparatus, there's an end load applied to the system, and there's a confining load. And this plane view of the stress, is identical no matter which way you look at the axis of the test specimen. That's why it's two-dimensional. But there's an important characteristic of this load in terms of the quantities we talked about that were stresses, right? There are normal stresses and there are shear stresses. This experiment is set up such that you're surrounded by a fluid, so there's no shear stress on the surface. It can't be because it's just the fluid load around it. The other load is an end-on load, straight end-on. So the only difference is this is confined in this direction, and you can increase the load in this direction. That produces differential stress. If I make this load equal to that load, I'm in just simple pressure. But as soon as I increase this load, I place differential stresses within the material, and that generates shear stresses within the substance. But in this reference frame, the reference frame of the experiment, there are no shear stresses. So if I were to write that matrix, I said of the components of the stress within the system, I got to find something to write with. What would that look like? The components of that quantity in a matrix form are just sigma, I'll give the number, meaning of this in a minute, sigma 1, sigma 2. This is, or I should say, end load, damn it. End load pressure, the piece of C, and these are 0, okay? Because there's no shear stresses. In this reference frame, there are no shear stresses, and these are differential loads. One of those has one quantity, the other has the other quantity. With your coordinate system set up in this system. So it's easy to determine, it's easy. That's a system that allows you to quantify the stresses within the system. So I already said some of this. You convert it to stress, right, by just measuring the end load force divided by the area, cross-sectional area of the system gives you the stress on the end of the system. And the confining load is just, you measure it with a pressure gauge, right? So it's easy to quantify the experiment. So what that means is that you could, relative to this quantity we just talked about, if you have a reference plane A or a reference plane B, and this one could be anywhere along this test specimen, those loads, those planes have no shear stress across them. All planes that lie perpendicular to the test specimen have that same load, and all planes that lie parallel in the axis of the test specimen have that same load, and no shear stresses on them. That's a very special, here we go, jumped ahead of myself. If you think about any other plane that might be within this particular system, that shouldn't really be true, right? You can just think about it as the vectors on them, these two vectors across one of these surfaces, and there's going to be a load that's applied to those systems. That's applied, there'll be a shear component that's added on to that particular plane. But what are those? How does that vary? That's the real question, right? How do you know? Sure, that makes sense. So how do I know what it really is? Without proof. You can show theoretically that these two planes, A and B, the two that are the reference planes in the experiment, always exist in any stress state. They're artificially set up within an experiment, but regardless of any stress system, you can always define a pair in two-dimensional stress, a pair of mutually perpendicular planes in 3 dimensions, three mutually perpendicular planes that have this property where there's no shear stress across that particular surface. Those are called the principal planes of that system, and the direction that's perpendicular to that plane is a so-called principal direction. All other surfaces have a shear stress across them, but it varies systematically, and that's what we're going to talk about. In the, I should have scrolled sort of ahead there. That systematic variation is related to what's called the transformation law for all tensors. It's exactly the same that strain would use, because it's related to the same, they're the same kind of physical property. They obey the same mathematical rules. I'm not going to make you learn the transformation law of tensors, but we can show it graphically in a very straightforward way by this graphical representation called Moore's circle. And it's related to the relation, and it's all related to the relationship between these mutually perpendicular planes, the so-called principal directions, relative to the variations in strain with different orientations. In geology, we customarily refer to these so-called principal directions, or different principal planes, as sigma 1, sigma 2, and sigma 3, where sigma 1 is the maximum principal stress, so the plane that has the largest normal stress across it. Sigma 2 is the intermediate one that has this intermediate value for normal stress across it. And sigma 3 is the smallest. It's the least compression across it. But remember, each of those principal planes has no shear stress on it. It's equivalent, it's the strain equivalent of the axes of the ellipse, the strain ellipsoid, where there were no shear strains. Remember? You take the box and squash it, you just get the same effect. This is geometrically equivalent to that. But in this case, it's the forces, not the geometry. So let's do this graphically and consider it this way. And I'm going to do this. This is on Blackboard. You can look through this. This is the system you can deal with. Sorry, it's an ancient old figure that I've scanned, but it works. If you have this, imagine if you will, this is that cube cut in cross section. The cube has the same values in any direction. So any cross section of the cube is just a pair of planes that are one side of that cube. And I'm going to arbitrarily cut the cube along a different direction. So what I want to know is what the values are for the normal stresses and the shear stresses on this face relative to these two reference faces. So if I know these quantities, these four quantities, two normal stresses and a shear stress, these are the same value. remember. So you have 3 values represented as this matrix. I can take these and I can do a force balance, because force over area, I can take the area times the force, and I get a force in this direction, I get a force in this direction, and I can have to balance that by the force in this direction, or it's going to move, right? So I can do that. I'm not going to spend a lot of time on this. All you do is set this up this way. Each of these faces is related to the angle, where there's a reference angle that you could think of this as a new coordinate system, of XY coordinate system relative to the old coordinate system. So in that direction is the normal to this plane. So this is important to realize, this angle theta is the angle between this reference direction and the plane. I want to know the values for the shear stress, and the normal stress. Oftentimes we use the word, or the Greek letter tau for shear stress, and sigma for the normal stress on a given surface. We'll see why that is in just a moment. When you do that, you do a force balance. I'm not going to go through all this trig. It's just a trig problem. You got a bunch of trig functions. The force on the new direction is balanced by this. You go through a bunch of trig, and you get this pair of equations for the normal stress and the shear stress values. It's a simple relationship in that it's just the stress on the new position is, or the normal stress on that condition is just a function of the angle between the 2 reference planes. So this is the sigma xx, sigma yy, those were the 2 normal stresses. This is the shear stress. And theta is just the angle from the plane. Fair enough? And the same, you can do the same kind of trig values and show the values for tau by the same force balance. This is a pure graphical way, or not a pure graphical, just a force balance representation of what's called the tensor transformation law. It's related to sines and cosines. And I'm not going to worry you about that, but that's all there is, right? Bunch of trig. You can look at that. If you like trig, you can figure that out quickly, right? Now, the simpler way to do this, what am I doing here? You can also, oh, that's right. You can also use this for an arbitrary set of values. You can determine with the unknown theta, you can actually calculate the orientation of where a principal system might lie relative to this by this general relationship. So you have a pair of values of sigma and tau on these 2 different surfaces. You can also use that indirectly to determine the orientation of where the principal directions lie. Don't worry about that for the moment. The more important one lies here. What does this have to do with this thing we call Mohr's circle? Well, Mohr's circle just takes that derivation I just did right there and turns it around and says, okay, I don't care whether I have an arbitrary orientation where there's sigma and tau for these 2 different values. I want something I can use relative to this deformation experiment, where I set it up so that my experiment has sigma and or has sigma 1, the compression direction, and sigma 2, the minimum stress direction, are the principal values. Well, if I do that, my experiment, this analysis we just did is simpler, because instead of having two values here, in the sense of sigma xx and sigma xy on each plane, there's only one value. There's sigma 1 in one direction, the maximum compressive stress, and the other one is sigma 3, the minimum principal stress. There's no tau to worry about. So now I can just do that, except the hard part has already been done, which is to do the trig. You just plug those into that other set of equations and go through a lot of trig, right? But including, it's not that much trig, but it's just you have to make use of what are called the double angle formulas, because it gets an ugly looking expression. And what you end up is, what is all that really matters for this whole discussion, is right there. Maybe go down a little bit so I don't have to stand on my tiptoes. There are a pair of equations that the first equation says sigma, remember that's the resolved normal stress on this arbitrary plane, that's relative to the principal system. So it's relative to the experiment, right? So sigma equals sigma 1 plus sigma 3, or sigma 3 plus 1 over 2, plus sigma 1 minus sigma 3 over 2 times cosine 2 theta. And tau doesn't have that extra term, but it has sigma 1 minus sigma 3 over 2 times sine 2 theta. Now, who are my mathematicians here? For a moment here, oh, I already said it here. These define, this is remember what parametric equations are? Or do you want to forget that from your math courses? This is a pair of parametric equations in what you might call stress space, where you could call this x and this is y. So the parameter is theta. So you have an xy plot relative to a parameter theta, but the parameter theta has a relationship. If you drop that one off, this is a x equals a function of cosine, and y is a function of sine. What does that define? And they have the same quantity in front. It's a circle. Simple, that's it, right? It's if I can find a piece of.
Oh, it's more circle.
It's more circle.
So just to confirm, everything that prefaced that is more leading into the proof into the final two equations and not something we're really actually going to use on a regular basis? Or do we as geologists actually do all of that trig on a regular basis?
Geologists can use it. So you can, coming out of this are things that you can actually use in the field, literally, in terms of interpretation of rock dynamics. That's where we're headed. But this also allows you to understand more about how stresses work and how material works.
Okay.
But let me just do this way and show you what I mean. Drop off the first term, this term here, for a second, and just put sigma equals r cosine 2 theta. Or in fact, let's make that psi. And that r. So r is sigma 1 plus sigma, sigma 1 minus sigma 2. Make that this becomes r. It's the same term in front, sine 2 theta, or psi. Cosine sine, that with no other parameters, that's r. That's r cosine theta, or cosine psi. That angle is psi. And that one is r sine psi, right? That's why it's a pair of parametric equations in sigma and tau. Cosine, sine. You never thought the unit circle was going to come back to haunt you, did you? But what's different? What's different from that simple unit circle relationship? First of all, r is this quantity. And the other thing is the angles are doubled. So you go around the circle twice as fast in this derivation. So when theta, the real theta equals 180, this is 360. So in 180, you've already gone all the way around the circle. Okay, so what is that? That's one part of it. It's a doubled angle. But there's another term here. This term, sigma 1 plus sigma 3 over 2, is shifting, right? That would be like, instead, that's sigma equals a plus r cosine 2 theta psi, I'm sorry. A would shift that, a, right? That's why that's what I mean by parametric. And there's no parameter like that in y, so it never leaves the x-axis. That's the nature of this particular beast, right? What's next? Okay, let me finish this. Actually, turn that off in